Good morning to all. I am Mrs.G.Lokeshwari, Assistant Professor in Computer Science, A.D.M College for Women, Nagapattinam. Let us see the topic is concurrency in operating system. Concurrency, mutual exclusion and synchronization. Then multiple process. Central to the design of modern operating system is managing multiple processes. First one multi-programming, second one multi-processing, third one distributed processing. Multi-programming, the management of multiprocessor within a uniprocessor system. Multiprocessing means the management of multiprocessors within a multiprocessor. And third one, distributed processing, the management of multiple processors executing on multiple distributed computer systems. Concurrency encompasses a host of design issues including communication among processes, sharing of any competing for resource such as memory, files and input-output access, synchronization of file activities of multiple processes and allocation of processes time to processes. The next, concurrency. Concurrency arises in multiple applications, structured applications and operating system structures. First one, multiple applications. Multiprogramming was invented to allow processing time to be dynamically shared among a number of active applications. Second one, structured applications. As in the extension of the principle of modular design and structured programming, some application can be effectively be programmed as a set of concurrent processes. Third one, operating system structure. The same structuring advantages apply to system programs, and we have seen that operating systems are themselves often implemented as a set of process or threads. The next, interleaving and overlapping process diagram. The process may be interleaved on uniprocessor in the diagram. The next, interleaving and overlapping process, and not only interleave but overlapped on multiple processor also. Next, then difficulties of concurrency. First one, sharing of global resources, managing resources, locating programming errors. First one, sharing of global resources. If two processes both make use of the same global variables and both perform reads and writes on the variable, and the order in which the various reaches and writes the executed in critical section. Then second one, managing resources. It is difficult to the OS to manage the allocation of resources optimally. Then third one, locating programming errors. It becomes very difficult to locate a programming error because results are typically not deterministic and reproducible. Then the simple example, a void echo opening brace CHIN equal to get care of, CHOut equal to CHIN put care, CHOut then closing brace. A program that will provide a character echo procedure. Input is obtained from a keyword, one keystroke at a time. Then each input character is stored in variable CHIN, then it is transferred to variable CHOut and finally sent to the display. Any program can call the procedure repeatedly to accept user input and display it on the user screen. Next, a simple example on a multiple processor. Process P1 and a process P2. A process P1 CHIN equal to get care of, CHOut equal to CHIN put care of, CHOut. Then same processes occurred in process 2, CHIN equal to get care of, CHOut equal to CHIN, then put care equal to put care of CHOut. The result is that the character input to P1 is a last before being displayed, and the character input to P2 is displayed by both P1 and P2. Enforce single access. If we enforce a rule that only one process may enter the function at a time, then P1 and P2 run on separate processes. While P1 is inside the echo procedure, P2 invokes echo because P1 is still inside the echo procedure. Therefore, P2 is supported awaiting the availability of the echo procedure. Then third, at a last time, process P1 Process P1 completes execution of echo, exit the procedure and continue executing. Immediately upon the exit of the P1 from echo, P2 is resumed and beginning and executing the echo procedure. Next one is race condition. A race condition occurs when multiple processor threads read and write data items. They do so in a way where the final result depends on the order of execution of the process. The output depends on who finishes the race last. Operating system concerns what design and management issues are raised by the existence of concurrency. The operating system must keep track of various processes, allocate and deallocate resources, protect the data and resources against interference by other processes, ensure that the processes and outputs are independent of the processing speed. Competition among process for resources. There are three main control programs. First one is need for mutual exclusion, second one is deadlock, third one is starvation. First one, mutual exclusion. It is a critical section in mutual exclusion. Suppose two or more processes require access to a single non-shareable resource such as a printer. During the course of execution, each process will be sending commands to the input-output device. It is important only one program at a time allowed to its critical section. Then second one, deadlock. Two processes waiting for the same resources, neither will receive the resource that it is already owns until it has acquired the other resource and performed the function requiring both resources. The two processes are deadlocked. Third one is starvation. The operating system may grant access to a number of processes while another one process. The next, requirement of mutual exclusion. Only one process at a time is allowed in the critical section for a resource. The process that halts in its non-critical section must do so without interfering with the other process. No deadlock or starvation. A process must not be delayed access to a critical section when there is no other process using it. No assumption are made about relative process speeds or number of processes. A process remains inside its critical section for a finite time only. The next, hardware support. Disabling interrupts. Uniprocessor only allow interleaving. Then interrupt disabling. A process runs until it invokes an operating system services or until it is interrupted. Then disabling interrupts guaranteeing mutual exclusion will not work in multiprocessor architecture. The special machine instructions are compare and swap instruction. It is also called a compare and exchange instruction. Then this is the example of compare and swap instruction. Integer compare and swap, integer asterisk var, integer test value, integer new value, opening brace, then integer old value equal to asterisk var. If old value equal to test value, word equal to new value, return old value. The version of the instructions checks the memory location asterisk var against a first value. If the memory location current value is test value, it is replicated with new value. Otherwise, if it is unchanged, the old memory value is always deferred. Thus, the memory location has been updated for the return value is the same as it is the test value. Next, a compare is made between and memory value and a test value. If the value differs, then swap occurs. The entire comparison of compare and swap function is carried out automatically. It is not a subject, it is an interruption. The next diagram about mutual exclusion. This shows a multiple mutual exclusion protocol based on a user of the instruction. A shared variable is bold. It is initialized to 0. The only process that may enter to critical section is one that ends of the equal to 0. All of the processes, the entire that critical section go into a busy waiting mode. The next exchange instruction. This diagram is about exchange instruction. The exchange instruction content of a registration with that of a memory location. Both the Intel A32 architecture and a 64 architecture contain a JCHG instruction. This shows a mutual exclusion protocol based on the user of an exchange instruction. A shared variable bold is initialized to 0. Each process uses a local variable key that is initialized to 1. The only process that may enter in critical section one that finds both equal to 0. It excludes all the process from the critical section by setting both to 0. When a process leaves to critical section, it restarts both to 0, allowing another process to gain access to the critical section. The next, hardware mutual exclusion advantages. Applicable to any number of processes on either a single process or multiple process sharing main memory. It is simple and therefore easy to verify. It can be used to support hardware mutual exclusion critical sections. Then between waiting consumer process time, it is a process while waiting for access to a critical section, it continues to process the time. Starvation is possible when a process leaves a critical section and more than one process is waiting. When a process leaves a critical section and more than one process is waiting, the selection of a waiting process is arbitrary. Then deadlock is possible. Deadlock is possible means example is uniprocessor system. The process P1 execute a special instruction, then P1 is then interrupted to given a processor to P2, then P2 now attempt to use the same resources of P1. Thus, it will go into a busy waiting loop. However, P1 will never dispatched because it is not lower priority than another ready process to P2. The next concept is semaphore. The semaphore is an integer value used for a signaling among processes. Then only 3 operations may be performed on a semaphore, all of which are atomic. First one, initialize. Second one, decrement. Third one, increment. The term ACM wait operation decrements the semaphore value. If the value becomes registered as negative, then the process executing as same wait is blocked. Otherwise, the process continues the execution. Then same signal means the operation increments the semaphore value. If the resulting value is less than or equal to 0, then a process blocked by a same wait operation if any is unblocked. This is the diagram for semaphore primitive. Next. Then binary semaphore primitive. A more strict semaphore which may only the value of 0 or 1. A similar concept released to the binary semaphore in the mutex concept. A key difference between the two is that the process that locks the mutex, then the value is 0. In contrast, if it is possible, one process to lock a binary semaphore and another one for unlock it. The next one, strong or weak semaphore. A queue is used to hold process waiting on the semaphore. In what order are process removed from the queue? For both counting semaphore and the binary semaphore, a queue is used to hold process waiting on the semaphore. The question arises the order which processes are removed from such a queue. The removal privacy policy is first in, first out. That is called a strong semaphore. A removal process is that has been blocked the longest released from the queue. A semaphore that does not specify the order in which process are removed from the queue is weak semaphore. The weak semaphore don't specify the order of the semaphore mechanism. Example of strong semaphore mechanism. The diagram represents example of strong semaphore mechanism. It is a example of semaphore mechanism. In this diagram, C begins to run off S but is blocked when it issues a same wait instruction. Similarly, A and B run are blocked into the semaphore, then allowing D to resume the execution when D has a result. It issues a same signal which transforms C to the ready queue. Then cycle of D will release A and B from the blocked state. The mutual exclusion using semaphore. This diagram shows straightforward solution to the mutual exclusion problem using a semaphore. Considering n process identified in the array of which need access to the same resources, each process has a critical section used to access the resource. In each process, the same wait is executed. If the value of S becomes negative, the process is blocked. If the value is 1, that is decremented to 0 and the process immediately enters the critical section. Because S is longer position and no other process will be able to enter B in critical section. Next. That is producer-consumer problem. it is a general situation. One or more producers are generating data and placing this in a buffer. A single consumer is taking items out of the buffer one at a time. Only one producer or consumer may access the buffer at any one time. In this producer-consumer problem, ensure that the producer cannot add data into full buffer and the consumer cannot remove data from empty buffer. This is the diagram of buffer. Producer-consumer problem occurred in the buffer. The producer can generate items and store them in the buffer in own pace. Each time on index n into the buffer is incremented, the consumer proceeds in a similar fashion but must make sure that it does not attempt to read from an empty buffer. Then this diagram about semaphore. The semaphore sometimes cleaner the solution can be obtained if general semaphore, also called counting semaphore, are used. The variable n is now a semaphore. Its value still is equal to the number of items in the buffer. Suppose now that in transcribing the program, a mistake is made in the operation send signal and send signal are interchanged. This would record that the send signal operation is performed to the producer official section without interruption. Would this affect the program? No, because the consumer must write on the both semaphore before proceeding in any case. The next one is bounded semaphore diagram. Finally, let us add a new and realistic restrictor to the producer and consumer problem, namely that the buffer is finite. The buffer is treated as a circular storage and pointer values must be operated in modular the size of the buffer. The next diagram about semaphore. This is some few examples. The next, message passing. The message passing means this is a communication about the process interaction. When process interact with one another, two fundamental requirements must be satisfied. First one is synchronization, another one is communication. The process need to be synchronized. It afford mutual exclusion cooperating the process may need to exchange the information. One approach to providing both of this function is message passing. The message passing has the further advantages, that is tends to implementation of distributed systems as well as shared memory multiprocessor and uniprocessor systems. The actual function of a message passing is normally provided in the form of pair of primitives. One is send, another one is receive. Send, destination, message, receive, source, message. These primitives are a minimum of operations needed for process to engage message passing. A process send the information in the form of a message to another process designated by a destination. Next one, receive. A process receive information by executing the receive primitive, including indicating the source and the message. The next, synchronization. Synchronization means communication requires the synchronization. Sender must send before the receiver can receive. Communication of a message between two processes implies some level of synchronization between the two. Receiver cannot receive a message from until it has been sent by another process. What happens to a process after it issues a send or receive primitive? Enter the sending process is blocked until the message is received or it is not. Similarly, when a process issues a receive primitives, there are two possibilities. First one, if a message has previously been sent, the message is received and execution continues. If there is no waiting message, then either first one, the process is blocked until a message arrives. Second one, the process continues to execute abundantly the attempt of the receive. Then blocking send and blocking receive. Both sender and receiver are blocked until message is delivered. This is known as rendezvous. Allows for tight synchronization between the process. Then non-blocking send. More naturally for many concurrent programming tasks, the non-blocking send, blocking receive. Although the sender may continue and the receiver is blocked until the requested message arrives. This is probably the most useful combination. It allows a process to send one or more messages to a variety of destinations as quickly possible. A process that must receive a message before it can do useful work needs to be blocked until such a message arrives. The non-blocking send and non-blocking receiver, neither the party is required to wait. The next concept is addressing. The sending process needs to be able to specify which process should receive the message. The addressing is divided into two types, then direct addressing and indirect addressing, and first one, direct addressing. Send primitive includes a specific identifier of the destination process. Receive primitive could know ahead of time which process a message is expected. The receive primitive could use source parameter to return a value when the receive operation has been performed. Then indirect addressing. The messages are sent to a shared data structure consisting of queues. The queues are called mailboxes. One process sends a message to the mailbox and other process picks up the message from the mailbox. This is the diagram for indirect process communication. A one-to-one relationship and many-to-many relationship. Then one-to-many relationship and many-to-many relationship is described in the diagram. A one-to-one relationship allows a private communication link to be set up between two processes. A many-to-one relationship is useful for client and server instruction. One process provides service to a number of other processes. In this case, the mailbox is often referred as a port. The third one, one-to-many relationship allows for one sender and multiple receivers. It is useful for application where a message or some information is to be broadcast a set of processes. Then fourth one, many-to-many relationship. It allows multiple server processes to provide concurrent server, then multiple clients.